Today we're covering 2.4, which is the math to go with the graphs and the models we've been developing so far for things that move at a constant velocity. So let's start with the definition of how to get average velocity. And that is something we've talked about already, I think, which is the slope of the position versus time graph. That's one way to get it if you have the graph. So because we would put position on the y-axis and time on the x-axis, but then in physics we would not use the x and y, we would use the variables that stand for those things. In this class, we use D for position, so that's kind of lame, but it is what we use. So we would put change in position, which is also known as displacement, right? And then change in time on the bottom, and then we get our formula for velocity. You see this bar over the V, okay? Oops, sorry, my pen is gonna drag that over. But that is supposed to mean average. So sometimes I remember to put that, but a lot of times I forget to write that. So it's not a big deal if you don't put that down, but that's what that means. Okay. Velocity is a vector, so it has a direction, and we use the sign to indicate that, which means that you would have set up a particular direction in the first place to be the positive direction, like north or east usually. Later on, when we get to studying things that go up and down because of, or that fall because of gravity, we will be talking about like using the vertical direction too. Okay, but then what if the position time graph isn't linear, like in some of the videos that you studied, like the little ice puck going down the ramp or the rocket taking off, right? So you will see, if that's the case, that the position time graph might curve, like the one in this slide. So you can still take average velocity, but it just doesn't represent how fast that thing is moving at any particular time. It is just an average. So I'm going to try to draw on here and explain. So if I'm taking average velocity like between these two time points, what I'm really doing is calculating the slope of a straight line between those 2 points, which is sometimes useful. I mean, you know that it was going maybe faster at the beginning and slower at the end. That's what it means when it like levels off like that. But it can be nice to know what was the average. Okay. Average speed is different. So there's a couple situations we need to talk about. If the velocity isn't changing, like you just have something that's just going down the street, the car is driving down the street, it's not changing direction, then all you have to do to get the speed of that car is take the absolute value of the velocity. Because we say that speed is a scalar, we don't care about the direction, we just want to know how fast. So easy peasy, right? But if something is let's say going around the racetrack, right? Then like its displacement would be 0 maybe. We talked about that in a worksheet. So you wouldn't ever say that a race car has a speed of 0. Like, you know, it might have a velocity of 0 because it didn't end up having a displacement, but it's definitely gone distance. It definitely has a very fast speed. So then, because we want to get the average speed, we will take the total distance over the total time. and calculate all the distance it's gone. Okay. So let's do an example here. And I labeled some points. I've got 5 seconds. This thing is at 11 meters. You can see that on the graph. And then at 8 seconds, it's at 5 meters. Okay, so it's going in the negative direction. That's what that negative slope means. So we can get the average velocity of that object between 8 and 5. So all we would do is get the slope. So we would do rise over run. We'd go 5 minus 11. Okay, and I'm getting average velocity here. Meters over 8 minus 5 seconds. Okay, so then I'd get 6 meters over, or sorry, that's negative, right? Be careful. Over 3 seconds. So if I simplify that, that's negative 2 meters per second. Easy. Then what's the average speed of that thing during that time? Well, I'm calling that a simple journey. That graph has not changed direction. It's a constant slope during that time frame. So I know it hasn't changed velocity during that time. So all I have to do is take the absolute value of my previous answer. So then the speed is just 2 meters per second. Okay. What's the average velocity of this object between 0 and 8? Okay, now I've got a different point, so let me kind of clear this out. Let's label this point. At 0 seconds, it is at 1 meter. Okay. Well, then all I care about for average velocity is just displacement over time. I don't care how the fact that it like went up all the way to 11 and then back down 5. Don't care. So all I do is basically take the slope of this line. Okay. So I'm doing average velocity is equal to 5 meters minus 1 meter over 8 minus 0 seconds. So that's a positive number, right? I'm getting 4 over 8 meters over seconds. So 1/2 meter per second. Another way to say that is, how fast would I have to walk, let's pretend this is a person, in order to get to that final spot if I didn't do all that, crazy walking around? I don't need to do all the forward and backward. I can just go straight there nice and slowly, okay, and get to that same spot. And then last question, what is the average speed of this object between 0 and 8? That's harder. I mean, not that hard, but now I need to know the total distance that this person has gone or thing and give them credit for all that. So, let's get this clutter out of the way. Except I still need to know that they started at, this is 0 seconds and 1 meter. So in the first, 5 seconds, right? They went this whole 11 meters. So the total distance, I need to know that, is 11 meters plus, then they went from 11 to 5, so that's 6, okay? And then how long did the whole thing take? It took 8 seconds. That's how I'm going to do the total distance. So that's, oh wait, but they didn't go 11, did they? They went from 1 to 11. So oops, that's 10 over 10 plus 6. That makes it nicer to divide. So 10 plus 6, 16 over 8 is 2 meters per second. Okay. All right. And then let's talk about instantaneous velocity. That is how fast you're going at an instant, right now. Okay, which might be different from how fast you're going right now. Okay. If your position time graph is a line, a diagonal line, then your velocity isn't changing, right? But if it's a curve, then this is harder to do. You would have to find the slope of the tangent line, okay? That requires calculus, so you could take AP physics next year if you're a junior, or you can take physics with calculus in college. That's pretty great, okay? And then this is on the next page, actually. This is beyond where I thought we would go. But if you want to write down this equation, this looks a lot like y equals mx plus b, only I guess it's, well, yeah, mx plus b. It's because we've got a final position here. That's what this means. df means, the f means final, okay? So final position equals, and then you've got the slope of the line is the velocity. The x, remember, on our x-axis we have time, or change in time. Sometimes I forget to write the delta sign. And then plus where you started from. That's your y-intercept. So that's your initial position. So in this class right now, we are going to focus on constant velocity problems. And so that's why I'm focusing on a linear function right now. And then in the next chapter, we'll get to do the quadratic ones. Okay,